Hi everyone, welcome to Pre-Calculus Lesson 9.2 and 9.4. We're talking about the dot product today. So let's talk about what a dot product is. It's kind of our substitution for multiplying of vectors. Technically, we can't multiply vectors, but the dot product is our solution to that. It's like another operation that mimics what may occur if we were allowed to multiply vectors. So basically what happens is you take the corresponding components from your vectors and you multiply them together. So I would do A times C and B times D, and then I would add those two products. Now that's going to result in a number, not a vector. Now if you're working in 3 dimensions, you would just have A1 times B1 plus A2 times B2 plus A3 times B3. So that's how a dot product works. Now let's talk about some of the properties of dot products. Okay, the order of the dot product does not matter. So if I do U dot V, it's going to equal V dot U. Now, if I have scalar multiplication of a vector, and then I take that result and do a dot product with another vector, it's the same as if I do U dot V and then multiply that by my scalar, or if I move the scalar to the V vector. Okay, so the order of that doesn't really matter. I can do vector addition and then do the dot product with a vector, or I can do the dot product with each vector and then add them, and it's going to give me the same result. And finally, if I do U dot U, so a vector with a dot product with itself, it's going to equal the magnitude squared. Okay? So those are just some properties. We don't use them often, but they're nice to know just in case something comes up. Let's take a look at an example next. In our example, we're given vectors. U is 3, -2, and V is 4, 5. We need to find the dot product of that. In part B, they give it to us in terms of the unit vectors, but we can still do a dot product. And then here in parts A and B, we're doing dot products with 3-dimensional vectors. So pause this video, see if you can find those dot products, and then press play to see if your answers are correct. Okay, in part A, U dot V, we would do 3 times 4 plus -2 times 5. Now 3 times 4 is 12, and 5 times -2 is -10. If I add those together, I get 2. For part B, I would do 2 times 5 plus 1 times -6. So that's 10 plus -6, which is 4. With our 3-dimensional vectors, I would do -1 times 6 plus 2 times 5 plus 3 times -1 to get -6 plus 10 plus -3 is 1. So 1 is our result there. And finally, we have 2 times -1 plus -3 times 2 plus -1 times 8. So you would get -2 plus -9 plus -8, which is -16. So let me know if you have questions about that. Most people find the dot product pretty easy, but let's take a look at some applications of it. Those can be pretty difficult. Let's take a look. So we're going to start by looking at the dot product theorem. If I know the angle between U and V, and I know their magnitudes, I can find the dot product using this formula. The magnitude of U times the magnitude of V times the cosine of the angle between the two vectors. And that's going to be the dot product. Now, if I wanted to, I could solve to find the angle between the vectors simply by dividing by these two magnitudes. So U dot V divided by the magnitudes multiplied together, and then I can do the inverse cosine to find the angle. So let's try applying these to some examples. In our first example, they want us to find the angle between the vectors U, which is 2, 5, and v, which is 4, negative 3. So we're going to be using that second formula, the cosine of theta equals the dot product of u and v divided by the product of their magnitudes. So my suggestion would be is to find the dot product, find the two magnitudes, and then put those numbers into the formula. So pause the video and see if you can do that, and then press play to see if your results are correct. For u dot v, I got 2 times 4, which is 8, plus 5 times negative 3, which is negative 15. When you add them, you get negative 7. For the magnitude of u, I did 2 squared plus 5 squared, and the square root of that, which is the square root of 29. And for the magnitude of v, I got 4 squared plus negative 3 squared, which comes out to be 5. So now I just put it all in the formula, negative 7 divided by 5 times the square root of 29. And then I did the inverse cosine of this fraction, and it came out to about 105.1 degrees. And that's the angle between our two vectors. Let's talk about another classification for vectors. Vectors are orthogonal if they are perpendicular. That means that the angle between them is 90 degrees, or pi over 2. And if they are orthogonal, then their dot products will be 0. So that's a good way to determine if two vectors are perpendicular or orthogonal. Now, I know that's a unique word, but it's kind of fun to say. So try saying it a few times, and then when you do say it, you kind of sound really smart. So it's a good word to add to your vocabulary. Anyway, let's take a look at an example question. In this example, we need to determine whether the pair of vectors are perpendicular. So do the dot products, and if they equal 0, then you know the vectors are perpendicular. If they aren't, then you know they're not perpendicular. So try and do that, and then press play to see if your answers are correct. In part A, my dot product was 3 times 2 plus 5 times negative 8, which comes out to 6 plus negative 40, which is 34. So these are not orthogonal. In part B, I did 2 times negative 1 plus 1 times 2. And negative 2 plus 2 is 0. So yes, these two are orthogonal. Let's take a look at another example. In this example, we need to show that the vector u is perpendicular to vector v. So we're still using that information about orthogonal. See if you can show that, and that means show all your work, and then press play to see if your work was correct. So I did my dot product, 2 times 5 plus 2 times negative 4 plus negative 1 times 2. That comes out to 10 plus negative 8 plus negative 2, which is 0. So these vectors are perpendicular. Let's take a look at another application of dot products. This one is called the component of u along v. And I like to think of it in terms of this picture where there's a bright light up here shining down, and vector u up here is giving a shadow on vector v down here. And that shadow is what we can call the component of u along v. So essentially, it's the distance along this v vector made by the u vector. So if I drew a straight line down to v and it's perpendicular to v, it would be the distance that I would be from the starting point of vector v. Okay, now to find that component, we do the magnitude of u times the cosine of theta, where theta is the angle between the two vectors. And this component would be negative if theta is more than 90 degrees, because if theta was more than 90 degrees, the vector would be pointing in this direction. And then the component of u along v would be negative because it goes beyond the initial point of v. And so it would be considered a negative, I guess you could call it a distance. Now you can calculate this component using a dot product. It's u dot v over the magnitude of v. Okay, so we have two formulas, magnitude of u times the cosine of theta, or we can find it using u dot v over the magnitude of v. Let's take a look at an example. In this example, it says, a car weighing 3,000 pounds is parked on a driveway that is inclined 15 degrees to the horizontal. They want us to find the magnitude of the force required to prevent the car from rolling down the driveway and find the magnitude of the force experienced by the driveway due to the weight of the car. So what I've done is I've drawn us a picture to help. The W vector is the weight of the car. That represents the force of the earth pulling down on the car. Now, U is the vector that would be the car's desire to roll down the driveway. And V is the vector that describes the force experienced by the driveway. So that would be the perpendicular force to the driveway. Now what I did is I drew this dotted line, that's the horizontal, and this is the 15 degrees they gave us in the question. Now I found this 75 degrees by just extending this and remembering that this weight vector for the car is perpendicular to the horizontal because it's pulling directly down into the earth. So this is 90 degrees right here. So I just found this 75 degrees using what I know about triangles. Now, I also know that this driveway and this vector describing the force on the driveway meet at a 90-degree angle. So if this is 75, then this also has to be 15. So that's how I found all of those measurements. Now let's talk about what they want us to actually calculate in our question. I need the magnitude of the force required to prevent the car from rolling down the driveway. Rolling down the driveway would be this way. This is the weight of the car that's pulling down, and I need the component of W along U because the weight of the car going in this direction is what I need. So pause the video and see if you can find the component of W along U. To find the component of W along U, I used the magnitude of W, which is the 3,000 pounds that my car is. And I also used the angle between the two vectors, 75 degrees. So I know that that is 3,000 times the cosine of 75. So the component of W along U is 776 pounds. Now we're going to do something similar, but I need to find the component of W along V to find the weight experienced by the driveway. Okay, so pause the video, see if you can do that, and then press play to see if you're right. So what I did is I did 3,000, which is the magnitude of W, times the cosine of 15, because that's the angle between the two vectors, and that's 2,898 pounds. Let's do one more example with this. In this example, they want us to find the component of U along V, but they've given us the component forms of U and V. So we're going to use the second formula, which was U dot V over the magnitude of V. So see if you can do that, and then press play to check your answer. I started by finding the magnitude of V. That's -2 squared plus 1 squared, and it's the square root of that. That comes out to the square root of 5. And then U dot V is 1 times -2 plus 4 times 1. So I had -2 plus 4 over the square root of 5. 2 over the square root of 5. And I rationalized to get 2 times the square root of 5 over 5. So that's the component of U along V. Now that's it for this video. You're going to have another video where we do 2 more different types of applications. So don't forget to watch that one.